Hello, we are looking at linear combination and spanning sets. We will start with linear combination. By definition, we say a vector v is called a linear combination. A linear combination of vectors v1, v2 up to vr. If it can be expressed in the form v to be equal to c1 v1 plus c2 v2 plus up to CR VR, where C1, C2 up to CR are scalars. What it means is that if we have a vector space, for instance, let's say this rectangle here is my vector space, and then in this vector space, I have V1, V2, V3, and then so many V's, so up to VR. Now, if I take any scalar and I multiply any scalar outside, that's C1, C2, C3, and then I'm able to find a linear combination that results into another vector in this one, then we are going to say that that particular vector space or vector is a linear combination. That is what we mean. Now we will take an example and see how it looks like when we talk about linear combination. Now we have an example here. It says determine whether 114 or 115 is a linear combination. So we are just going to apply the principle we've learned already to see whether it is a linear combination or it is not a linear combination. All right, so first we want to write the vector given to us, which is 114, and then we are saying that that is equal to the expression of this vector in the linear combination of this and this vector. So we have, let's say, c1 times 1, 2, -1, and then plus c2, 3, 5, and 2. So if you are able to find values of c1 and c2, that will result into this vector. Then we are going to say that this particular vector is a linear combination. So let's see. So we can form a series of equations from this one, where we can say that c1 plus 3c2 will give us 1 if you compare both sides. And that will be my equation 1. And then we'll have 2c1 plus 5c2. That will give us another 1. That will be our equation 2. And then the last one, we'll have negative c1 plus 2c2 will give us 4, and that will be our equation 3. Now, if we solve this equation simultaneously, or we use elimination, we can use substitution, or we can use the augmented matrix. If you are going to solve this one, we can use elimination. This one will cancel that. So using elimination, we are saying that equation 1 plus equation 3 will have, so when we are adding the two of them, we're going to have c1 plus negative c1, that will give us 0, and then 3c2 plus 2c2, that will give us 5c2, and then that will be equal to 1 plus 4, that will give us 5, and so we have c2 to be equal to 1. Now we substitute that into equation 1, and when we substitute that into equation 1, so sub into 1, we'll have c1 plus 3 to be equal to 1. We take it across and have c1 to be equal to -2. In order to see whether our solution that we've gotten satisfy all the three equations, we can test it with the second equation to verify. So if I do that, I substitute that, I have 2 brackets -2 plus, and then 5 brackets 1, and what am I getting? So I have -4 plus 5, and that'll give me 1, and so that is also satisfied. So we can see that we've been able to find a solution for c1 and c2, where c1 is equal to -2 and then c2 is equal to 1. And so we are saying that the equation or the vector 1, 1, 4 is a linear combination. So the same procedure we use in solving the second one, the second vector given to us, and then the second vector given to us is 1, 5, 1. So we have 1, 5, 1 should give us C1 times the first vector given to us, which is V1. That's 1, 2, negative 1, and then plus C2, 3, 5, 2. All right, so let me change the pen color. All right, so if I have this, I'll form a series of equations from this. And so if I form a series of equations from this, I'll have 1 to be equal to C1 plus 3C2. And then we'll have another one to be equal to 5 equal to 2C2, C1 plus 5C2. And then the last one, that is 1 to be equal to negative C1 plus 2C2. This is my equation 1, equation 2, equation 3. Now we solve them simultaneously, just like how we did the other one. And then when we add, so we use elimination again, using elimination. All right, so using elimination, when we add equation 1 and 3, we are going to have 2 to be equal to 5C2, right? And we divide 2 by 5, divide here by 5. We are having C2 to be equal to 5 over 2 over 5, sorry, 2 over 5. So this is what we have. Now we can use the 2 over 5 to find our C1. So we substitute it into equation 1, and then we'll have equation 1 to give us 1 C1 plus 3 brackets 2 over 5 to be equal to 1. So we do our math. We have C1 to be equal to 1 minus 6 on 5. And then if you do the calculation, you're going to have negative 1 on 5, negative 1 on 5. All right, so if we substitute that into the equation we have here, we are expecting to get 5, right? So let's do that. And so if I substitute, I'm going to have 2C1, which is negative 1 over 5, plus 5 bracket 2 over 5, and that should give me 5. But when I do that, I'll have negative 2C over 5, negative 2 over 5 plus 2, and that will not be equal to 5. We know that will not be equal to 5. And so this particular system has no solution. So the equations has no solution. So what do we say? We can say that 1,5,1 is not a linear combination of V1, V2. All right, so that is how we go about it. Now let's move on to another thing. So we are going to talk about spanning sets. What is a spanning set? Spanning set. If we have a set of vectors, that is V1, sorry, let me use a different pen here. So let me use blue. So if you have a different set of vectors, if you have a set of vectors, that is V1, V2, up to Vr, right? And it's any set of the vector space V. The set of all linear combination is called of the vector. So the set of all linear combination of the vectors is called their span. All right. So what it means is that if we have vectors v1, v2, v3, as we did in earlier stages, and then we are able to express all of them as a linear combination. Now the set of these combinations is what we call the span, and then we represent it by, so we can write it as span of v1, v2 up to vr. So we can write it as that. Now we are saying that v1, v2, v3 is called the spanning set. So we can write that. So if we can write this one, we can say that v is equal to the span of v1, v2 up to vr. Then we are saying that this particular set is called the spanning set of v. All right, so that is there is a relationship between spanning set and then the linear combination. If you can find linear combination, after finding the combination, the set of all these linear combinations is what we call the span of the set of the vector. Sorry. Now we look at some example on how to find the span, or to show whether a particular vector space has a span or not. So here we are going to use the standard basis of the vector space in Rn to solve that. So our solution, we say show that in Rn the span E1, E2 up to En, and they've given us E1 and E2 and En, and then we have that. So we are supposed to show that it is a span. So we move. All right. So what we do is that we must show that every vector in Rn lies in the span. We must show that every vector space or every vector in Rn lies in the span of E1, E2 up to En. So what we will do is that we let v to be equal to v1, v2 up to vr, right? So we have this, and then it is, so these are all vectors that they are arbitrary vectors in Rn. All right, so they are just in Rn. Now we know that we can write these ones as a linear combination. So in a linear combination form, we say that v is equal to c1 v1, right, plus c2 v2 plus up to cr vr. That is what we know. And so in our case, our vectors given to us is E1, E2. So we substitute that and we have C1, E1 plus C2, E2 plus whatever up to CR, ER. In our set is N. So please let's convert all of the R's into N in order to match the example given to us. All right. So if we can write it as this, we know E1, we know E2, we know En. So what we do is that we just substitute that and then we'll have V. So we have V to be equal to C1 times the space, the vector given to us. That is 1, 0, 0, all right, up to 0. So only the first term is 1. The rest are 0. Plus C2, 0, 1, 0, up to 0. So that is how it will continue like that up to En 0, 0, up to 1. All right. So this is what we have. Now when we multiply through by the scalar, we are going to get the scalar being in all the terms. And so we can say that v is equal to C1, C2 up to Cn, right? You can say that. Sorry. So here is supposed to be Cn. So we can say C1, C2 up to Cn. And that will be the same as writing what I wrote initially. That is C1, E1 plus C2, E2 plus Cn, En. Right. So since we have been able to show that these vectors that, or these scalars that we chose, they still lies in the span, we can just say that hence v lies in the span E1, E2 up to En. So that is how basically we will go about this one. All right, now let's move on to the last example for this session. And then the last example we are going to consider is that we should show that the polynomial is equal to the span of 1x, x squared up to xn. So how do we go about it? So it's a proof. We have to show. So the first thing is that we will consider the general form of a polynomial. And you know, by definition, the general form of a polynomial, so we say let Px be any polynomial. So Px be any polynomial we know. All the polynomials we know in this world. So any polynomial in Pn. All right. So in this case, by definition, we can say that Px will be equal to an xn, right? Plus an minus 1, xn minus 1, plus whatever up to a1 x plus a naught. That is if we consider all the general form of the polynomial. All right. Now, to show that it spans, we need to find the specific scalars. We have to find the specific scalars C1, C2, C3, such that if we take px to be equal to cn xn plus cn minus 1 xn minus 1, right, plus a1, sorry, it's not a1, so it's supposed to be c1, so c1 x plus c naught. All right, so that is what we have. So if we have these two equations, this is 1, so let me use a green pen here. So this is 1 and this is what? This is 2. So if I compare 1 and 2, I can see that we can see that cn is equal to an, right? And then we can say an minus 1 is equal to cn minus 1. And then we can also say it continues that way to say, sorry. So we can also say c1 is equal to a1 and a naught is equal to c naught. Since any polynomial in the form Pn can be expressed as a linear combination of 1 x squared xn, then we can say that we can conclude that it is the set spans. All right, so this is how we write it. So we can write it as, since any polynomial px that we choose in Pn in the polynomial can be expressed as a linear combination of what they give us, which is 1 x squared up to xn. Then we can say the set spans